Welcome to Snapshot Lectures in Chemistry. Essentially, chemistry for all. In this visual series, we will discuss chemistry content through the use of animations. Let's begin. The questions we seek to answer are: what is the rationale? Why should we care? And what is the story behind it all? So let's begin. Today we will be discussing reaction kinetics. We will be discussing reaction kinetics. And the model for the story, or the base of the story, is we have two superheroes arriving in the Bahamas. As they traverse through the traffic, they are learning about chemical kinetics. So let's begin. For this story, we see the two superheroes, Parakletos and Sophia, arriving at Linden Pendant International Airport to explore Nassau as they learn college chemistry. They travel through Nassau traffic with a tour guide named Maria. And what they come to understand is that car traffic is like a model for reaction kinetics. The rate of a chemical reaction is a measurement of the velocity or speed of a reaction. The faster the rate, the faster product formation. The faster the rate kinetically fast, that's what we're referring to. The faster the product formation, the slower the rate, the slower the product formation. That's if we're looking at the rate of reaction in the context of changes in product concentration over changes in time. So the formula for rate is typically described as the change in product concentration over the change in time, or the change in reactant concentration over the change in time. Now, the signs that we use in front of those fractions or equations is based on the rationale that rate by physical convention is normally positive. Now, what are the consequences of a reaction rate being in terms of the reactant? So some of the consequences for a reaction rate is that there will be a negative sign in front of it. The reaction concentration is decreasing, and that coincides with the idea of there being a negative sign there. Now, this level, by physical convention, is typically denoted as positive. The rate is typically denoted as positive. So key ideas to keep in mind, the reaction rate is determined by dividing the change in a molecule's concentration, which is in moles, or which is molar, by the time. And we can define rate as molar per second. So things to keep in mind. The final answer for rate is positive. So let's keep going. When you're calculating the rate of reaction, the scalar factor, in fact, is basically stoichiometrically based. So it's based on the number of moles. For simplicity, the definition of and determination of rate is reflective of the balanced chemical equation. However, one of the best predictions of rate of reaction is a series of experimental data in which the concentrations of the reactants are measured, as well as the formation of products. One of the first people to work on chemical kinetics was Ludwig Wilhelm. So let's keep going. Car traffic is similar to kinetics since it is directionally dependent and has limiting factors similar to chemical reactions. So for a set temperature and pressure in an open system with a constant supply of reagents, basically saying when you have constant conditions, the rate of reaction typically remains constant. So what is the significance of the car traffic model? It's similar to kinetics since it's directionally dependent. Traffic depends on the direction in which you're headed in, and it has limiting factors, such as obstructions in the road. But the limiting factor or the limiting step or rate limiting step for a chemical reaction is, or rate determining step for a chemical reaction, typically influences how we describe the rate law. So also, car traffic is dependent on the types of cars on the road. And same with chemical reaction, it's dependent on the substrate that's reacting. So as we can see here in this panel, the main idea is that rates of reactions based on experimental data is a probabilistic predictor. In chemical reactions, we determine rates by using concentration values over time for reactants or products. Now, what's so interesting about this is that we can get a snapshot picture of the reaction rate, and it's known as the instantaneous rate. For a series of products and reactant concentration plotted on the graph, the reaction rate is the rate at one point in time, or the slope at an instant. The rate is like the news. It tells us much more information about what has occurred in the reaction and cannot strictly or accurately predict the future just off of the balanced chemical equation. In other words, it helps us well to have a series of experimental data when we're trying to understand reaction rates for chemical reactions. Given the reaction rate is affected by variables such as light, heat, pressure, and concentration, it's important to measure those and see how they change in the reaction. And by measuring those, we can get an understanding of how the rate changes and even the rate itself. So light, as you know, in many reactions, some reactions are catalyzed by light. Heat plays a role in increasing temperature of reactions, and that has implications for reaction rate as well. Pressure, the more pressure you put on a reaction vessel, has a capacity to affect reaction rate. And concentration, as we see based off the definition of rate, the concentration of a reagent influences reaction rate. Now it depends on whether the reaction or the rate law is for zero order, first order, second order, or other orders. But at this time, just know the concentration influences the reaction rate. Now, when we have different variables for light, we can use this UV spectrophotometer. For heat, we can use a bomb calorimeter. For pressure, we can look at a barometer. And for concentration, we can also use a UV vis spectrophotometer and a mass spectrometer. So let's keep going. An apt description of a rate of reaction is a rate law, with the caveat that the rate of the reverse reaction must be negligibly slow. We're speaking kinetically. So for zero order reactions, we know that it's independent of the concentration of the substrate, where the order is zero. That typically is rate can be described as K, or rate can be described as independent, as I said, of the concentration. Also, the consequences of a zero-order reaction is that the concentration of the reactant decreases linearly with time and with constant conditions. With any concentration of substrate, the rate is constant. The rate is constant, simply put. So it's important to recognize when you have a zero-order reaction. Now let's talk about first-order reactions. The rate of the reaction is directly proportional to the concentration of A, which is typically a linear relationship. Of course, for all of these rate laws and orders, there are integrated rate laws, which are linear representations and linear descriptions, which incorporate a relationship between concentration and time. So, the consequences, let's look at the consequences for a first order reaction. It is that the rate is directly proportional to concentration. It's a linear relationship, typically. So let's talk about second order reactions. For a second order reaction, the rate of the reaction is proportional to the square of the concentration of the substrate. Also, the consequence of a second order reaction is that rate is more dependent on the reaction concentration. It is proportional to the square of the concentration of the substrate under observation. Let's keep going. One of the ways to determine the rate of reaction is through the use of the method of initial rates. And what that really entails is when you're given a series of experimental data, you basically use the first thing you do, you take the given data, you look at how the concentration is changing in relation to how the rate is changing, you come up with with an understanding from that, and then you use the equation where rate is equal to the change in concentration of the reagent over the change in time. And we're using the equation, using the experimental data, and seeing how it changes initially, you start to determine the order of the reaction, and from that you can denote the rate law. Typically, when we determining rate law, we look at the slow step or the rate determining step, because that influences how fast the reaction is able to go to completion or to product formation. So when studying these things, it's important to understand the rules of exponents and logarithms. And simply put, the logs play a role in simplifying rate laws, and the laws of exponents play a role in helping you to work out the answers. That's very important. So the other things to consider: half-life. When the concentration of a reactant falls to 1/2 of its initial value, the time required for the decrease is called the half-life. There are formulas to describe the half-life for each order. It's important to know those. As well as we can understand the temperature dependence of the reaction rate to the constant K. Using our Arrhenius equation, we can relate frequency factors, exponential factors, and activation energy to the constant K. E of A is in this equation. The equation is described or denoted as K is equal to A, E raised to the minus E, A over RT, where EA is the energy barrier that must be overcome for reactants to produce product. The RCD, or reaction coordinate diagram, shows a peak, and that peak typically represents the activation energy barrier. You can go into other ideas in which we talk about Hammond-Leffler postulate, in which we understand that as we look at the transition state intermediate, it typically represents the step that's closest to it in potential energy, as well as for Arrhenius plots. We have the collision model, which basically is a theory that says that chemical reaction is based on sufficiently energetic collisions occurring between two reactant molecules. From this, we proceed onto ideas of molecularity, which we have unimolecular and bimolecular, and this goes right into ideas of organic chemistry, in which you have substitutions which are bimolecular or unimolecular. Overall, reaction kinetics is a very important topic. Differential equations can be used to study this idea. However, for general chemistry levels and for high school chemistry levels, it's easily understood through the doing, through the experimentation, through the watching a reagent transition in terms of change of color, whether it's a qualitative experiment in which you look at the change in color, or quantitative experiment in which you measure the amount of product formation over time. Those play a large role in helping to understand this concept. Once again, this is a snapshot lecture of chemistry concepts.